When the average is a 75 and there's nobody in the 70s, that's a problem. But it was clearly a doable exam. If you're down here, go through this one because you'll see these things again. And let's figure out what happened and how we can fix it so that next time it's easier to do.
I think honestly, just like the last preparing, I think of the last one I prepared for like a week and a half before. I think it definitely showed. And this one I definitely procrastinated, so definitely on that one.
Okay, whack, whack, whack. Sure. That happens. I understand. It's completely reasonable because, hey, all of a sudden, it's like, oh, wait a minute, it's Thanksgiving. I had an exam to study for. Oh, yeah, I get it.
But there's totally good life. There's no curveballs. I think everything it's like everything was all the best. So
Oh, I knew there was one curveball, but that's why I made it the bonus question. Because there was nothing on the review sheet about making models.
yeah.
And I'm like, wait a minute. I did 3 sections on modeling. I should put a model question on here. I didn't tell them to prep for that. Make it the bonus. And then I cheated and stole it from an old exam, an old textbook. So I'm like, oh, I even have one I can use.
I think if I could figure out my sign errors, I think I do pretty well.
That would definitely help. Sign errors are a big thing. And when they're big sign errors and they cascade, it's a big problem. But when it's like, all right, circle that -1.
Yeah. It's kind of time.
Oh, yes. This
Yeah.
was I have an hour to do this? Crunch.
Yeah.
Although that is part of why in the complex one, I gave you the eigenvalues and eigenvectors. It's like, okay,
Yes.
here, take it from this because doing that in complex variables isn't intuitive. And unless you really like complex numbers, it's not something you do a lot of.
Yeah, that was nice. So, yeah.
So we've done a lot of integrals. We've done a lot of differential. What comes after integration? Oh, right. Series comes after integration, just like in Calc 2. Oh, okay, wait a minute. A power series is basically an infinite version of a polynomial. A is the point where we center our power series. And the CNs are just numbers. There are coefficients. It is quite frequent. We'll use A equals 0. When I do use A equals 0, my power series is just CNX to the n. But this is really a bunch of individual numerical series. And I go all the way back to Calc 2 and I say to myself, what does it mean to converge? Oh, right, I got to do that limit of partial sums thing. But we define this limit as the limit of the sum going from little n equals 0 to capital N, and then we let capital N go off to infinity. And that idea is that I will just take more and more closer and closer approximations. And when I plug in x0 for my x value, I either get a number, a finite value, or I get this limit doesn't exist or it blows off to infinity. If it is a finite value, we say this converges. Otherwise, it diverges. But if I'm writing this series in terms of just a variable x, I want to know which x zeros converge and which don't. Well, it would make sense for me to call this the set of convergence. But it turns out this set is always an interval. And that interval will have A at its center. So we start at A, we go to the left by some number, we go to the right by some number. So A minus R, A plus R, and it may include one or the other or both endpoints. Sometimes it's easier to write this interval as thinking it's the set of x's that are some distance from A. But on a number line, that looks the same. And if I put a less than or equal to, I get both endpoints. If I only get one of them, I'll usually use the less than, or I'll write it out this way and include whichever endpoint I need. It is possible that R could be 0. The only place we converge is at the point A. It's possible that R could be infinity, which means we converge everywhere. That's fine. Page 241, figure 611. I see several options for our interval of convergence. The third one down uses the right end, but not the left. The fourth one down uses the left end, but not the right. Familiar concepts. We did this in Calc 2 a long time ago. We did this in complex variables if you took that, but most of you didn't. So it's been a while for most of us. So this absolute value shows up in a lot of other places. Frequently, we talk about the absolute value inside my summation. If this converges, then we say that the original one without the absolute value converges absolutely. Or is absolutely convergent. If you take that interval and you come in just a little bit, then every series that converges absolutely on the interior of the interval of convergence. Now, this is a technical sentence. Because you might think if you were to take the limit as little r gets closer and closer to big R, that this would continue to be absolutely convergent, but that isn't true. This is not an absolutely vital part of what we're going to do most of the time. There are specific exceptions where this rears its ugly head and beats me over the head with a stick. And I promise, unfortunately, we will see them next week. Because it is precisely those places where really weird and interesting stuff happens. In the engineering universe, those are the points I'm actually interested in what's going on. How do I find R? How do I figure out where a series converges? A power series in specific. My favorite series test from all of Calc 2. Taylor is a type of series. Yeah, I did all those comparison tests. But which one was the one we used that was the most powerful that we used for Taylor's series? Yes. Yes, it was forever ago. Given a series, I don't even need to know what the index is. Given a series, I want to define a value. Let L equal the limit as n goes to infinity of the absolute value of the ratio of consecutive terms, an plus 1 over an. If L is less than 1, then the series converges absolutely. If L is bigger than 1, then the series diverges. If L is equal to 1, this test is inconclusive. This is called the ratio test. This works for any series. It doesn't have to be a power series. But if I do this with a power series, when I do this L, I get an expression that has X in it. Here is a power series. The sum of x to the n over n squared, or 1 over n squared x to the n. Let me write out this expression for L. I start with an plus 1. That means I take this expression and I put an n plus 1 in it. Then I put that over the expression as it was written. And now a crap ton of algebra. Let's simplify this. What happens with my x's?
Should the X and Y cancel?
Yeah, And that'll leave me 1x in the numerator. But what happens with the fractions involving n? Fraction on the bottom. Pull it out, flip it over. So I'm going to get n squared on top and n plus 1 squared on the bottom. And I'm left with 1x and it's on the top, so I just set it off to the side there. Wait a minute. Does x care what happens to n? So I can take the absolute value of x and put it out in front here. Oop. There we go. Now, if I can figure out what happens to this limit, I'm much happier. What happens to this limit?
It goes to 0.
Does it? Wait a minute. When n is 5, I get 5 squared over 6 squared. That's 25 over 36. But then it's 36 over 49. And then it's 49 over 64. And then it's 64 over 81. Those don't look like they're getting smaller.
So if you find a way to factor x out, especially in your calculators, yes, instead of just see where it converts to in the table.
I absolutely could. But the problem is with that is I may have to go way out on that table, right? So let's do it analytically instead. This, I can think of it like it was a polynomial, right? If I multiply out the bottom, I get this, right? And I am taking the limit as n goes to infinity. Now, since n is a positive number, the absolute value here really doesn't mean squat on the n's. It does mean something on the x's. And now I go back, quite a ways. Not even to Calc 1, but all the way to the algebra class I took before Calc 1. Or I think about when we did limits in Calc 1 that went off to infinity. Or I think of discrete and I think of big O notation. The top is big O of n squared. The bottom is big O of n squared. Those are growing at about the same rate. This limit turns out to be 1. Only the highest power matters. The other way we did it back in calculus was what we said is, I'll go 1 over n squared and 1 over n squared. I'll multiply by 1, right? And then this will be the limit 1 over 1 plus 2 over n and 1 over n squared. And since n is going to infinity, what happens to these two pieces? When n gets really, really, really big. Which means that as we go to infinity, those actually do have a limit of 0. So this limit is 1, which means there's still that absolute value of x, right? This is my L. This is L. Our series converges when what?
When it equals 1.
Oh, look carefully. Not when it's equal to 1, but
Oh, wait.
when it's less than 1. So I know this sum, 1 over n squared x to the n equals 1 to infinity, is absolutely convergent when x is less than 1. In absolute value, that's my radius of convergence. I now know my interval looks something like this. Except, Cody, what happens when my limit L is 1?
It's inconclusive.
Oh, crap. So that means when X is either -1 or 1, this test doesn't help me. I need to check those two special. So I need to check the ends of the interval. What happens if I put in X equals 1? Then this series, n equals 1 to infinity, 1 over n squared, 1 to the nth. What's 1 raised to any power? Yay! That's what this is equal to. So now I have to ask, does this converge or does this diverge? And Hayden, here's where I need all the rest of those convergence tests. So this is the problem part of this chapter. I got to go dig up the entire chapter 11 pile from the calc book from however many years ago you took calc 2. Okay, drop an F-bomb here. It's appropriate. All right, what are we going to do? 1 over n to a power. I remember a whole category of series that looked like this. It was 1 over n to a power, so we called them 1 over n to the p, we called them p series. And there was a rule about p series when they converged and when they diverged based off of the integral test. I know some of you are going, I've heard this before, but I don't remember. And that's the whole point of this, to remind you that you have learned these things and you can go back and find them. A p series has the property that it converges if the power p is bigger than 1. And it diverges for the rest of them. Which means, what do I know about this one? Yay! So now I know I can include 1. 1 is part of my interval because we converge there. What about -1? Okay, when I put in a -1 here, 1 over n squared, I get -1 to the n. I'm going to rewrite that as the sum -1 to the n over n squared. And that -1 to the n, again, kicks me in the back of the head and goes, I remember something about this. What's that -1 to the n thing do to a series? Every term changes sign. We gave that a name as well. Say again? Alternating series, exactly. And we have a test for alternating series. Does it alternate? And if I take the minus away, does the limit go to 0? Alternating series test has two components. One is 1 over n squared decreasing. As n gets bigger, what happens to 1 over n squared? Is, without the minus sign, is it decreasing? Because as n gets bigger, the bottom is getting bigger, the whole fraction is getting smaller. And then is limit, as n goes to infinity, 1 over n squared equal to 0. Which means, since both of these answered yes, this converges. And that means that the interval of convergence includes both ends in this case. Sometimes one of these converges, sometimes neither of them converge. Sometimes both of them converge, as we see here. But this is going to require me to remember like half a dozen other series tests. P series, alternating series, geometric series, the integral test, the comparison tests. We had a limit comparison. There were a whole bunch of these. But they're all basically big O ideas, which is my benefit. I can think of this in discrete terms as well. Whew. Shall we do another one?
Sure.
3 or 5?
5.
Okay. Sum n equals 1 to infinity minus 1 to the k over 10 to the k x minus 5 to the k. That series is as k goes from 1 to infinity, not as n goes from 1 to infinity, because there aren't any n's in the freaking problem. I changed the letter. Big deal. Let's do the same thing. Set up your limit L for the ratio test. So I write out the fraction exactly the way we've written the term in the series, with k plus 1 replacing k on the top and leaving it on the bottom. Okay. What happens? I could, but I could also just look at what they do with the tops as well. Could?
You get all the K's, pretty much all the K's are going to
Yeah, because here, what's going to happen?
It's just be an exponent. Here's to be to the first one.
Right, which is just one of them, right? And then this 10 to the k down here and this 10 to the k up here is going to leave me a 10. And it's on the bottom in both of those fractions, so it'll be on the bottom in this fraction. But then what's the absolute value of minus 1 to a power? No matter what the power is, right? Because when I take minus 1 and I raise it to a power, it's either positive 1 or negative 1. And the absolute value is always 1. So those turn into 1s. Hey, wait a second. That means this becomes 1/10 absolute value of x minus 5. When does this converge?
No, it's less than.
Which means 1/10 absolute value of x minus 5 less than 1 means the absolute value of x minus 5 is less than 10. Okay, wait a second. The center of my interval is 5 because it's x minus 5. And then I go 10 and 10. My radius of convergence is 10. So that means if I subtract 10, I'm at -5. If I add 10, I'm at 15. Now I have to check the ends. I just copied down my series again because I was going to take the piece of paper away and I wanted to have the actual series sitting in front of me. Which end do you want to do first, the left or the right? Okay, so if I put in -5, then I get -1 to the k, 10 to the k. What's inside that parenthesis?
Negative again.
Aha. Oh, wait a second. Isn't that the same as -1 to the k, 10 to the k? Because I can think of the -10 being multiplied together, so I do the negatives first and then I multiply by the tens. Like I distribute the k power to both the minus sign and the 10. What happens here? What happens here?
Negative.
But -1 to an even power. Always, that's 1 every time, which makes this the sum of 1. I'm sorry, these are k's. K equals 1 to infinity. K equals 1 to infinity. What happens when you add up infinitely many ones? Which is not a finite number, is it? Poof. So this diverges. What happens if we do the other end? Plug this 15 into here for x, which means I get an alternating because the 10 to the k cancels the 10 to the k, and I get -1 to the k. K goes from 1 to infinity. And that definitely alternates, right? So how do I check the alternating series? Take away the -1, what's left? Just a 1, right? So answer me this question. Is 1 decreasing? And as soon as I answer no, I can stop. As a matter of fact, if I think of adding this up, I go -1 plus +1 plus -1 plus +1 plus -1 plus +1. Not really. Well, -1 and +1, that's 0. And then I get another -1 and another +1, and that's 0. I can't. If I take the -1 out at the beginning, then I get +1 -1, that's 0. My answer should be -1. Is my answer 0? Is my answer -1? It turns out that somebody actually tried to say you should average these, and the correct answer is -1/2. That's up. No, no, no. This diverges, and we're going to walk away from it.
Is that the one thing where it's like proving that, some certain series that's like, I think it could be equals 0 or maybe they said it equals like -1/12 or something.
That's one of the string theory problems. If you add up the numbers 1, 2, 3, 4, 5 off to infinity, that goes to infinity. If you believe in string theory, the answer is -1/12. How do you add up all these positive numbers and get -1/12? I'm not stoned enough for that to make sense. But the string theory guys, they like it. Dealing with divergent series and dealing with infinity in general is what makes people think mathematicians just make crap up. Because infinity is not just weirder than you think it is, it's weirder than it can possibly be thought to be. No, just say it diverges and walk away. Yes.
How'd you get -5 and 15?
Our center is 5. Add 10, subtract 10.
Okay, so we don't like worry the negative sign for it.
Oh no, it's x minus 5, right? So the distance from x to 5.
Oh, okay.
And so it's from x to +5. If I had x plus in there, it would be x minus a negative.
Okay.
Since I'm thinking of distances, I always want to think as distance as subtraction. The other way I can do it is I can do it the way by rewriting this is saying, oh, well, -10 less than x minus 5 less than 10. And then I add 5 to everything like that.
Okay.
Page 242, example 1, does one in the textbook as well. Okay. Back in Calc 2, I said that when I have a power series on the interval where it converges, that's actually a function. So this particular expression is some function of x between -5 and 15. Outside of that, it blows up to infinity, and I don't know what's going on. But between those two, I could graph this. It's a function. On the interval of convergence, a power series defines a function. And here is the absolute best part about all of this. That function is continuous, differentiable, and integrable. And in order to find the derivative or the integral, I can do that term by term. Now, what does that expression term by term mean? Well, let's use the power series we were just looking at. I can think of my function f of x as being defined by this, excuse me, by this series. Well, this is just a whole bunch of crap added together. If I tell you to take the derivative of x squared plus cosine x, you take the derivative of the x squared, you take the derivative of the cosine, and they're separate from one another, and then you add them together. I'm adding a whole bunch of crap together. I want to take the derivative. F prime of x is the total of the derivative of this thing. I just took a derivative. I left the coefficient alone, and I took the derivative of x to the k. So I get kx to the k minus 1. That's power rule, baby. I like that. You could do it again. You could take the second derivative. Like that. You could integrate the integral of f of x dx. Means I just integrate one at a time. So I would get minus 1 to the k over 10 to the k, and then I would get x minus 5 to the k plus 1 over k plus 1. Oh, right, and there should be some giant plus c at the end. I'm doing an integral, there better be a plus c. Holy moly, I can do them one piece at a time. That's the best thing about power series, is that they behave just like polynomials on steroids. Most of the time, now you'll notice this particular power series started when k was equal to 1. But the general power series that I wrote started when it was equal to 0. Let me look at this again for a second. If I do y equals the sum cn x to the n goes from 0 to infinity. That's a power series centered at 0. This is the same as c0 plus c1x plus c2x squared plus c3x cubed, and so on forever. What happens when you take the derivative of this? You just use power rule over and over and over. What's the derivative of c0? So the first term goes away. And I can think of y prime as now starting at 1 instead of at 0. Exactly. Or if we started at 0, we'd think of the first thing as being 0, and the second thing as being 0, right? Because we have that, right? So this power doesn't become 0 until we get to 2. Otherwise, you'd have an x to the minus 1 and an x to the 0, but the coefficients on both of those would be 0. And that makes my life work. This is called an index change. And sometimes we actually want to put the index back. So I think as much as I like the fact that that starts at 1, I think I might be happier if it started at 0 the same way this one did. But I'd need to shift all of these. This is basically a U substitution. I'm going to replace N by M, where M is 1 smaller. Oh, so this becomes M plus 1 x to the M. So I've replaced M with N into M minus 1. And then this will be C. Oh, it'll be M plus 1. And then this will start where M is 0 to infinity. We just shift our index a little. Now, here's the part that makes most people unhappy. Most of the time in all the textbooks, when they shift the index, they don't bother to change the letter. So they would take this exact expression and write that. And if I'm looking at this and I'm looking at that, that's annoying. But this is y prime. But by changing the index so that they match, I'm lining them up. The reason for doing this is to do arithmetic. If I wanted to add y and y prime, I could do that now. Why would I want to add y and y prime? I don't know. What's the name of this course again? So I'm doing equations with derivatives. Damn it, I'm going to do equations with derivatives. Y plus y prime is one of those kinds of equations. A couple of things to remember again from Calc 2. Power series are unique. On a given interval, with a given center, there's only one representation. If you move the center, you change the representation, but there's only one. And that means that if I have a power series equal to 0 on some interval, the only way that works is if all the coefficients are 0. If there's a unique representation and the answer I get out is 0, then all the coefficients have to be 0 all the way through. Homogeneous differential equation, right? If y prime minus y equals 0, well, then I can set up the coefficients and I can figure out what the coefficients are. And once I know what the coefficients are, I can figure out what power series that is. A function is analytic on I if f of x has a power series representation on the interval I. So we're talking about starting with a function and getting a power series for it. The types of functions we can do that for are called analytic functions, which, by the way, is why the broader class that contains calculus and differential equations and all of this study of mathematics is called analysis, because it deals with analytic functions. That means that all those Taylor series and Maclaurin series that we did back in Calc 2 are analytic. Page 243. They stole this directly out of the calc book. With the exception of these two for the hyperbolic cosine and the hyperbolic sine, all of these were in the calc book. We don't do the hyperbolic functions in Calc 2 anymore. We only really use them here, and it's easier to write stuff in terms of E, in my opinion. And if you take a look at it, e to the x, we did this just the other day, right? With our matrix exponential. So I know that one. And then cosine and sine, hey, look, those are the even ones, those are the odd ones. That's why cosine's an even function and sine's an odd function. And here's a tangent, arctangent, which is also odd. Here's the logarithm. Logarithm can't be centered at 0 because ln of 0 is undefined. So we do it at ln of 1. That's why it's 1 plus x. And here's a geometric series, x to the nth. I'm not expecting you to memorize these, but you should write these on your formula sheet. They're really useful. Page 243. And yes, you're doing series and analysis. You're doing series and complex. As a matter of fact, you're doing them the past couple of weeks. So we've just done these. You did these in a bunch of classes. You can adjust, by the way, a series to represent another function. Since I know that e to the x has this series on the interval from minus infinity to infinity, I could say, I don't want to look at e to the x. I want to look at e to the 3x. How would I write a power series for e to the 3x? Actually, if I want to put the 3, it's got to be with the x. So it's going to end up being up here. Which really means I didn't multiply by 3, but I actually multiplied by 3 to the n within the term. And guess what? That converges minus infinity to infinity. It is possible to add, subtract, multiply, or divide power series, as long as they have the same center and the same index. That's why reindexing is so important. I want to reindex so I can do this kind of arithmetic, this kind of combining. Without reindexing, this gets really, really unpleasant. Now, I'm the first guy to tell you this ain't pretty. But it's really just the distributive property. We wrote down e to the 3x right there, yes? Cosine of x is the sum n equals 0 to infinity 1 over 2n factorial x to the 2n. Please let me have written that down correctly. No, I didn't. I forgot the minus 1. Minus 1 to the n. It's an alternating series. I should remember that. My apologies. If I want to add these, well, you'll notice that this is only adding even numbers. This has even and odd numbers in it, so it's a little harder to do as a series. But what I could do is I could write out the first 4 or 5 of each of them. E to the x plus cosine x is 1 plus, oh, sorry, e to the 3x. 1 plus 3x over 1 plus 9x squared over 2 plus 27x cubed over 6, right? Because it's 1 factorial, 2 factorial, 3 factorial. And then I have cosine of x, which is when n is 0, that's 1 over 1 x to the 0. When it's n equals 1, it's minus 1 over 2 times 1, 2 factorial, x squared, plus 1 over, that's plus because it's minus 1 squared, 4 factorial is 24, x to the 4th, and then I can just gather all my like terms. And now it becomes a question of how far do you need to go for the situation you're dealing with. You need to go out to x to the 5th, x to the 6th, x to the 10th. You can go as far as you want. If I wanted to multiply these, I'd be distributing for a long time, wouldn't I? I tend to write this when I do this as a table. Right? And I just gather all my like terms when I'm done. Again, normally you'll be told how far you need to go. Maybe I only need to go to x to the 4th, which means I could ignore this part. But it's going to depend on how far you need to go. Same thing with division. If I'm doing division, I'm going to do long division. Long division sucks. So I'm going to try and do it as infrequently as possible as I can get away with this. But if I want to add or subtract, and they have different indices, I need to adjust the index, like we saw earlier. I'll need to do a U substitution for the n somehow to make everything line up so I can get this combination better. There's an example on page 244 to 245 that does this reindexing. Example 3. Pay close attention to that one. Okay. Why? Why are you doing this to me? I promise I'm not doing it for the hell of it. Now, here's the best part. I already know how to solve this. I do. This is separable. So I know what the answer should be if I do it that way. But I'm going to assume I don't know separable. And I'm going to say, well, there should be some function where this works. Let's suppose that I had a power series for that function. Now remember, that is the same as saying that I have C0 plus C1x plus C2x squared plus C3x cubed, and so on. What's the left-hand side of this equation? Well, that's y prime. Take the derivative of our power series. What do I get for that?
That's it. End of the one.
N equals 1?
Yeah, yes.
Okay, yes.
We need C and X to the N as well.
Great. Which is C1 times 1 times x to the 0 plus C2 times 2 times x plus C3 times 3 times x squared. Hey, look, that matches exactly what I want, right? This is supposed to be equal to x times that. This is the left side. Actually, let me write out a few more. 4c4 x cubed, 5c5 x to the 4th, and 6c6 x to the 5th. That's the left side. The right side is this with an extra x on it. C0x plus C1x squared plus C2x cubed plus C3x to the 4th plus C4 x to the 5th plus C5 x to the, and so on, right? I just added one extra x to each of those pieces. Guess what? The constant term on the left has to be equal to the constant term on the right. The x term on the left has to match the x term on the right. The x squared term on the left has to match the x squared term on the right. Let's just set them equal to each other. Okay, wait a minute. What is the constant term on the left? What's the constant term on the right? Ah, that's got an x on it. There isn't one on the right, so it's equal to 0. Ah, this is the constants. What about the x term? Let's look at the x term on the left. And the one on the right, those need to be equal. Okay, wait a minute. That means that C2 is C0 over 2. Okay. Let's look at the x squared term. X squared on the left. How about on the right? Wait a second. We know C1 is 0, right? That's what you said up here. So C3 is 0. Oh. What about the x cubed term? And on the right? Oh, wait a second. It's the x cubed term.
Sorry.
But C2 is C0 over 2. So that makes this C4 equal to C0 over 8. I have a sneaking suspicion that all of the odd ones are going to be in that left column, and all of the even ones are going to be in the right column, and all of the even ones are going to be in terms of C0. Let's do one more of each. X to the 4th. Over here on the left side, x to the 4th. And on the right, but we know C3 is 0. Every one of the odd numbers is going to work out this way. Even ones. X to the 5th term.
66. C4. So, C0 or something.
Hey, hang on a second. This over 2, right? I divided by 4 here. What if I wrote this differently? What if I wrote C4 as C0 over 2 squared and a 2? Right? Isn't that denominator 2 squared and 2? And this denominator is 2 cubed times 6. 8 times 6. But 6 is 3 factorial. And this 2 is really 2 factorial. And I can think of this as C0, 2 to the 1st, 1 factorial. I got a pattern here. For the even powers, c to the 2k is C0 over 2 to the k factorial. And for the odd ones, we always get 0. That means that my power series has this for a coefficient. Whenever it's odd, we get a 0. Whenever it's even, we get C0 over 2 to the k factorial, x to the k. Oh, wait a minute. This is only for the even ones. So it's only for the even ones, not x to the k, it's x to the 2k. Ready for a little bit of rearranging? I'm just going to shuffle the numbers here. Don't punch me, but I promise this is going to be amazing. C0 is a constant, pull it out front. This is to a k, this is to a k. So that's x to the 2k over 2 to the k. And then I have 1 over k factorial. If I multiply powers, I take the power of a power, right? So x to the 2k is x squared to the k. I'm just going to rearrange, put the 1 over k factorial for, oh, wait, I've written k now 4 times, and this is n. I need to replace that with k. This is my problem. I keep screwing up which letter I'm using. Now, here's the magic. I recognize this. And most of you are going, I sure as hell don't. That's right. But are you ready to see where I recognize this from? We wrote it down earlier. Thing to the n over n factorial. Thing to the n over n factorial. This is an exponential equation. As a matter of fact, this is C0 e to the x squared over 2. Which is exactly the answer you would have gotten if you did this by separating. We started this with the idea y prime equals xy. If I separate that, I get dy over y equals x dx. Integrate, I get ln of y equals x squared plus c. So I get y equals e to the x squared plus c. That's e to the x squared, e to the c. Oh, wait a minute, that's over 2. Helps if I do my integrals correctly, doesn't it? And isn't e to the, that's equal to number e to the x squared over 2. It's the same damn thing, isn't it? And I knew nothing about this before I started this problem, that it was going to work out so beautifully. I knew that because it was separable. If my equation's not separable, if my equation is an absolute bastard of an equation, and I say, well, let's see if there's a power series, what relationship can I find in the coefficients? And then can I make it look like a power series I already know? And even if I can't, I now have an analytic description, because I have a power series of the function that is my solution. I am begging you on bended knee, metaphorically, my knees hurt right now, to read this chapter and go back and read chapter 11 out of the calc book to refresh yourself on the series tests, because we need them. Because next week, after you get back from Thanksgiving, I got 3 more days of power series and then we're done. That's all that's left. I'll see you after the break. Enjoy yourself. Have a happy Thanksgiving.